Dear students, Assalamu alaikum and welcome back to Plant Physiology course. It has been a while since we last uploaded our video. So let's continue from where we left off. In the previous videos, we discussed the laws of thermodynamics just to get a concept of energy, what is energy, and how it can be utilized. So according to these two basic laws of thermodynamics, the first two laws of thermodynamics provide us some very important information, critical information as far as the energy of a system or energy is concerned. And according to the first law, we can transform energy from one form to another. And according to the second law, it is not possible to 100% utilize energy, as there will be some loss when we try to transform energy or when we try to do some work as far as the energy is concerned. In the previous video, we considered the third law of thermodynamics, and which states that absolute entropy is zero at absolute zero. But in plants or in plant physiology or in living organisms, we do not take into account the absolute values. We are mostly concerned with the relative values of a process, of a system, its initial state and its final state. Now, one important or valuable concept in this regard is the Gibbs Free Energy, which represent the amount of energy that is available to accomplish a particular task or a particular work. So we have Gibbs Free Energy. Although in the beginning I promised, so to say, that there will be no mathematical interpretation or there will be no mathematical work involved in the discussion of these laws of thermodynamics and energy, but we cannot totally ignore the mathematical equations or the mathematical interpretations which are concerned with these concepts of energy. So one of them is Gibbs Free Energy, and it can be represented by this simple or straightforward equation. So this Gibbs Free Energy can be represented as G, uppercase G. So Gibbs Free Energy is equal to E plus PV minus TS. Now what are these quantities, or what are these variables? In this equation, E is the energy and S is the entropy. T, it is the absolute temperature. And P, it is the pressure. And V is the volume. So this particular equation tells us the relationship of these various quantities: energy, pressure, volume, temperature and entropy. And E plus PV minus TS is equal to G, or the Gibbs Free Energy. Now, as far as the energy is concerned, let's elaborate these quantities or these variables somewhat. As far as E is concerned, or energy is concerned, now this is the internal energy or total energy. This internal energy is the sum of all the energies like electronic, rotational, vibrational, translational, kinetic energy and so forth. So all the energy, the sum of energies are total energy. This is E. Pressure P, mostly measured in bars, and this is pressure in ATM, that is atmospheres, or bar. As far as the volume is concerned, so we usually measure volume in liters. So volume in liters, and T is the absolute temperature, and it is 273.18 degrees plus C. And S is the entropy or the disorder that we have already discussed in the previous video. Now, as far as this Gibbs free energy G is concerned, usually it is not possible for us to calculate the Gibbs free energy as absolute values, exact or absolute value. It is mostly not possible. But as I stated in the beginning of the video, that we can study a process based on its stages or its states, the initial state and the final state, and the relative difference between its initial state and the final state, so which it gives us an indication or an idea about the energy in the system or that is being used in the process. So for that we usually use another quantity, a very common quantity in physics, that is del G or delta G. Now delta G is the difference in free energy of the system, of the process, its initial state and its final state. So delta G, in most cases it is equal to G2 minus G1. Now G2 is the final state and G1 is the initial state. Now delta G is equal to G2 minus G1, or the difference between the final states of the Gibbs free energy and the initial state of the Gibbs free energy. To illustrate this concept, or what do we mean by this difference in the free energy, we can take two very simple examples in which we try to move water from a higher level to a lower level, and we can also reverse the process. We can move the water from a lower level to a higher level. So here's the diagram showing the example, and we have two containers, one on the left and one on the right. On the left side we have water moving from container A to container B, and this is a downhill movement. As you can see here, the water is at a higher initial energy level, that is G1 is higher, and as it moves down through this siphon into container B or the second beaker, the energy is lost. Now this is a spontaneous process, and the final energy level of this container B, G2, it will be lower than G1. So this is an exergonic reaction, that is energy is released from the system. So the equation is somewhat like this: G2 minus G1 is equal to delta G, and as you can see we have a minus sign, and this minus sign indicates that energy has been released from the system. In the diagram to the right, this one, again we have a container A and container B, but now the movement of water is in opposite direction. And since the container B is at a lower initial energy level, that is its G1 is lower, so it requires certain input of energy to move the water uphill. Now the water is moving uphill and it requires certain amount of energy. And as the water moves from container B to container A in the reverse direction, in this system, container B has a lower energy level, that is G1. Now G1 is now that of container B, and the container A has a higher final energy level, G2. So when we try to calculate it, and this is an endergonic reaction. How do we come to know that this is an endergonic reaction? Because G2 minus G1 is now delta G but with a plus sign, and this plus sign indicates certain amount of input of energy, because G2 is at a higher level, and when we subtract G1 from G2, we get delta G with a plus sign, and this indicates an endergonic reaction in which energy is consumed or energy is utilized. The exergonic and endergonic reactions are quite common in living organisms and in plants, and these reactions are often related to various processes like assimilation, synthesis, breakdown, and we have various chapters dedicated to these processes like respiration, photosynthesis. Now this example illustrates the concept of delta G, as we have seen in the start of the video, or the equation is still here. Delta G is equal to G2 minus G1, and this gives us the difference in energy levels between the final state and the initial state, or the initial state and the final state. Okay, we have seen various states of the Gibbs free energy, G2 and G1 and delta G, and we have also seen that when delta G is with a minus sign, that is energy is being released from the system, or when delta G is with the plus sign, indicating that energy is given to the system or there is an input of energy. So what's so special about it? We are talking about diffusion and osmosis, and this is what we are going to discuss. So obviously these concepts are related to our process of diffusion. As we discussed in the previous video, the entropy, and we saw that second law of thermodynamics tells us a lot about the spontaneous process, and diffusion is one of them. Diffusion is a spontaneous process, it is a passive process, and it proceeds from a higher energy level to a lower energy level. So in terms of Gibbs free energy, the initial state of the system is at a higher energy level, and as the diffusion proceeds, the energy decreases and the final state of the system is at a very low state of the energy, or we say that diffusion has stopped or an equilibrium has reached. So these were the initial and final states of the energy, and as I said in the beginning of the video, that we are mostly concerned with the relative states of the energy instead of computing or calculating the absolute values. So in terms of second law of thermodynamics or entropy, the diffusion proceeds towards a disorder, or entropy increases, because, and this tells us that diffusion is a spontaneous process as it proceeds towards a disorder. And next, in terms of Gibbs free energy, we know that diffusion, when it starts, it is at a higher energy level, and as the diffusion proceeds, it moves down an energy gradient to a lower energy level. So this was Gibbs free energy and its various states and delta G, and how it relates to the process of diffusion. We haven't yet arrived at the conclusion, or where we can refine or make a better definition of diffusion, but as we are proceeding along, we are getting an idea that what happens when diffusion is taking place. So in terms of second law of thermodynamics, in terms of Gibbs free energy, at this particular time or moment, we now have a better idea of diffusion. So we are going to define diffusion in another way in the next video, and finally we are going to make its final definition in terms of energy. So thanks for watching, and see you in the next video.